Okay, so we introduced the whole idea of linear programming. This is a fairly simplified introduction. There's a lot more you can do with linear programming, but this is limited to the simple cases. But basically, it's an optimization tool which allows you to solve several optimization problems for different industries such as banking, education, forestry, tracking, and many others as well. It's highly used in the industry. So optimization is basically making the most effective use of a resource under some conditions, limitations, or constraints. So it may be like maximizing the profit or minimizing the cost and so on of some production process, or maximizing the yield of on a farm and so on. Usually the resources are limited, so you have to work with the limitations to come up with the best use of the resource. Like I said earlier, the techniques we work with here will just be limited to 2 variables, but in real life, you will work with many more than 2 variables. And to deal with more than 2 variables, you may want to work with this simplex algorithm developed by George Danzig in 1947. It works for more than 2 variables, and that is what we would use if you have more than 2 variables. This is beyond the scope of this talk, so we will not discuss the simplex algorithm in this talk. We will focus on graphical solutions to linear programming problems. So here are some what we would call the structure of a linear programming model. The first few things you need is you need to have the decision variables that will help you, will completely describe the situation or the decision to be made, along with the constraints. So the objective function will be the function that is to be maximized or minimized, or in one word, that would be the function to be optimized. So we'll be trying to find the values of the decision variables that optimize this objective function. So we also have a constraints. The constraints are just inequalities. So I may not cover that in detail, but within the problem being solved, that's where we shall cover that. The other concept we need is a feasible region, and this is simply all the points that satisfy the limitations of the constraints in the model. So a feasible region. So we need to solve a problem, we need to determine all these. And once we set them up, we can, in our case where we'll be working with only 2 variables, we shall be able to find the optimal solution using graphical techniques. So the best way to do this is to do an example, so we can go see all these concepts in action through an example. And our technique will be graphical solution. That's what we shall use to solve this. So here's an example. I'll leave it on the screen for a while. I'll read it out, but I can leave it for a little more time for everyone to read and internalize the problem. We can always come back to it if anyone wants us to come back. So this is from one of the past KCSE questions. I don't know, it was 2017. I will double check the year. So the question says a trader stocks 2 brands of rice, and that is A and B. He intends to order fresh supplies, but his store can accommodate a maximum of 500 packets. So he orders at least twice as many packets of A as of B. So he requires at least 50 packets of B and more than 250 packets of A. So if he orders X packets of A and Y packets of B, we are required to do the following. The first one is to write down all the inequalities that we satisfy the information given, and on the represent the inequalities on a grid. Here we shall I use them. I will work out. I drew the grid using GeoGebra, so I did not do this manually. But in an exam, I think you're supposed to do it manually. You'll be given a grid, and you'd have to draw that manually. Then the last part we are supposed to do is to maximize the profit that the trader can make, given that type packet A makes a profit of 12 shillings and B makes a profit of 8 shillings. So that's the problem we are supposed to solve. So we shall go one by one. We start with A, B, and followed by C. We may need to, from time to time, refer back to the problem so that we stay on track. So the first one we'll do is to write the inequalities of X and Y which satisfy the information above. I already done this in the next slide, but maybe we can try to go through it before we go to the next slide. So let's try to figure out what's going on here. So we try to figure out where the constants are within the problem and see which inequalities will be appropriate. So the trader intends to, so here, the first one is this: his store can accommodate a maximum of 500 packets. So we have X packets of A and Y packets of B. So in total, you cannot exceed the total number of packets ordered cannot exceed 500. So that would be the first one, and this would be a constant for the storage. So the other one says he orders at least twice as many packets of A as of B. So B is Y, and it should be less than or equal twice, I think 2x. So I need to write that clearly. So that's the other idea that we obtain from here, from this second statement. Then it says he requires at least 50 packets of B. So 50 packets of B means we need Y should be at least 50. So Y should be greater than or equal to 50. And then we have, we need more than 250 packets. So this should be a strict inequality. The keyword here is more than 250 packets of A. So A is represented by X. So we want X to be at least 250. So that gives us the whole set of inequalities that we need to work with. I think I will now go to the next slide where they are written, unless there are any questions on this. Okay. So so the next slide is here, and we as usual we need to determine the decision variables. In this case, already been given to us, and they are defined as the number of packets of A as X and the number of packets of B as Y. And we use them to work out the inequalities, which you already did. So all I have done here is repeat the inequalities. And this is what they would look like. So this gives us the complete set of inequalities that we need to work with. So the next part is to graph the inequalities. We'll go one by one. So the first, by graphing these inequalities, we'll be able to determine the feasible region or the set of all points that satisfy all the constraints. So we start with this first one, X plus Y is less than or equal to 500. And this will be the graph. So now we need to determine which is the unwanted region. We need to find the region with the points that satisfy this. Now to check this, the easiest way is just to pick one point on one side. And if that point satisfies the inequality, that's the side you're looking for. So you shade out the other side. You also need a boundary to make the decision. And the boundary will be at the point where X plus Y is equal to 500. So we first draw this line, X plus Y is equal to 500. Then check on both sides. Pick at least one point on both sides, plug it into the inequality and see which one works. So if you pick 0, 0 is on this side, 0, 0 satisfies this inequality. It doesn't matter which point you pick, any point you pick will be just fine. So it means any point on the same side as 0, 0 will be one of the wanted points. So we end up shading the opposite side. So we use the same ideas to find the other the graphs of the other inequalities. So the next one is this, no, it's X is greater than or equal to 2Y. So we can rewrite that as X minus 2Y is equal to 0. And here is the graph. So X minus 2Y is equal to 0 is the border. So again, you can check points on both sides to determine which is the unwanted region. We have shaded the unwanted region, so anything below this will satisfy our inequalities. So then the next thing is the next constraint is X is greater than, strictly greater than 250. So because this is a strict inequality, we shall plot the line X is equal to 250. And of course, anything that is greater than 250 will lie on the left, to the right of this line. So we shade out the side that is not needed. That's what we have. So we still have one more inequality, and that is Y is greater than or equal to 50. So again, our border will be Y is equal to 50. Once you have border, you can figure out which side you will shade it. So what is in the middle here, the feasible, the points that will satisfy all the inequalities. Anything outside this region will not satisfy inequality. So one thing to note also is that this is a strict inequality. X is greater, this region is X is greater than, now the, yes. Do you have a question?
No.
Yes, do you have a question? Just go ahead and ask. Can you hear me?
Sir, he left. Sir, the one who was asking you the question left.
No. Okay. So we can see it then. So we have the feasible region. Now, one assumption that that is made throughout this is that the variables are continuous. So sometimes you may end up with solutions that are not integers. So we will see how to deal with that in one of the cases. So we'll point out the following. The points at the corner are usually your optimal. If an optimal point exists, usually it will be on one of the vertices, or if you like, some people call them corners. So it may be a good idea to check if the values at the corners will optimize your objective function. Unless the values are not integers and you need integers, then you may have to change your strategy. All these other points in the unshaded region will also satisfy the constraints, but may not give you the optimal value for the objective function. So we need to obtain the objective function, and the objective function was the profit. We saw that, or rather the question says the profit from A was 12 shillings and the profit from B was 8 shillings. So each unit of X will provide 12 shillings, a total of 12X, and a total of 8Y for unit B. And this gives you the total profit from selling the whatever is in stock. So this is a quantity now we are supposed to maximize, and we usually call this the objective function. Now to find the optimal value, we can use what we call the isoprofit lines. We can assign an arbitrary value to Z. We could use values that are already in the feasible region to get a starting value for Z. And this will give us a search line. Now we can get more such lines by getting new values for Z. We do that by changing the values of X and Y. And as you get more and more values of Z, you'll do it in such a way that the profit keeps going up until you get the maximum profit. So since all the such lines are parallel, once you draw one, you can use a ruler and a set square. Yes?
How do you get the number 4,000?
I will get to the graph in a minute. You will be able to see it's you just pick values of X and Y that are in the feasible region to get you started. So if you take X to be 300 and Y to be 50, and you shall see this is a point in the feasible region when we go back to the graph, and then you plug them back into this profit. So the profit will be 4,000 if you have X of 300. 300 of type A and 50 of type B. So you just plug these values back in here to get write it out. Here you'll get 4,000.
Okay, so thank you.
So there's no reason why you must work with 4,000. Oh, you've seen that, eh? Yeah, so this is just, you actually can work with any pair of values that is in the feasible region, but I just picked 350 to start with. So that provides us our initial search line, and then we can move this search line to eventually identify the optimal solution. So now, as you move the search line, the last point that it will touch, you'll have to move it towards up and towards the right. The last point that it touches in the feasible region will give you the maximum value for the profit. So we shall illustrate this in a minute. So here is the search line in green. The graph is still as it is, and the search line is here in green. Now there are so many feasible points. This line is a strict inequality, so any point on this line will not be in the feasible region. I've tried to label all the other points that are in the feasible region. Here's a point which is fractional, yet we need integers. So this is what I was telling you, the assumption that it makes it that the variable is continuous. So sometimes you end up with some fractional values, but there are ways around it. So these are all the feasible. So one way to find the maximum profit would be by inspection. So you could compute the profit at all of these feasible regions and find the one that gives you the highest profit. That is one way. So, but the theory shows that if an optimal value occurs, usually it will occur at the vertices. So instead of checking all of them, you just inspect the points at the vertices. So by inspection, you can also find the maximum, but you simply check the points at the vertices. Here you can only use these two because these other two are not in the feasible region because we have a strict inequality here. We had a strict inequality where X was strictly bigger than 250. This region, yeah. So, but the equations I've put in here are the equations of the borders that separate the wanted and unwanted region. So maybe I will show how this works in GeoGebra. I will stop sharing this or start a new share. Okay. So I don't know if you can see my desktop. Can you see the GeoGebra open? Can you see anything, the green line moving?
No, sir. No, sir, we cannot.
No, sir, we can't.
Okay, I'll stop sharing again so that I share it afresh. So can you see my desktop now?
Yes, on my side.
You can see it there. Okay, fine. This was the first line we drew for the objective function, which passes through the, and which is one of the points in the feasible region. So we could have drawn this at any one point, picked any one point in the feasible region, and drawn the corresponding line to start off. So if you want to find the maximum value, you will have to move this profit line. Its last point in the feasible region. So you can see the last point it hits is this 450. And so this solution, so this is the optimal solution. I don't know if that is clear. So you could use a ruler and a set square to do this as well. So if you place a set square along this line and the ruler on this end, after placing the set square, you'll be able to move the set square in such a way that it will give you lines that are parallel to this starting line, this green line. And the last point where it hits the feasible region will give you the values for the optimal solution to the problem. Unfortunately, I can't illustrate using the straight edge and a set square on the computer, or at least I didn't prepare anything on that, but I guess it makes sense. I will go back to the slides now if there are no questions on this. So now I'll share the slides again. Maybe can someone confirm if the slides are visible?
Yes, sir, they are visible.
They're visible now.
Yes, sir.
So our problem is basically solved. We have found the values that will optimize the objective function. I did not calculate, but you can substitute them in here. So we have 12x. You can work that out and see what the optimal value is. We had, is it 450 and 50? So x is 450 and y is 50. So you would simply work this out, and then you'll get the maximum profit that will be made with this. So you can work this out. I will not work this one out. You will work it out in your own time. And 8 multiplied by 50. This will give you the actual maximum profit that the businessman can make. So this is plus. It doesn't look like a plus, but it is a plus. Okay, so we can move on to the next problem. So this will be the last problem we cover. So we'll read the problem again. It says a road contractor has to transport 240 tons of hardcore. This must be this material used for construction. So he will use 2 types of lorries, type A and type B. He has 3 of type A lorries and 2 of type B lorries. And the capacity of each type A lorry is 8 tons, while that of each type B lorry is carries 15 tons. So all type A lorries must make the same number of trips, and similarly, all type B lorries must make the same number of trips. So each lorry makes exactly the same number of trips. For each different type of lorry makes the same number of trips. So we're told the number of trips made by each type B lorry should be less than twice those made by each type A lorry, and each type A lorry must not make more than 6 trips. So this is all the information we have. We have the questions to be answered. So the first question we need to answer is take X to be the number of trips made by each type A lorry, and Y the number of trips by each type B lorry. So these are the decision variables. They've already been given to us. We don't have to look for them. So we need to prepare all the inequalities in X and Y to model the problem. One, we will need to draw the inequalities on the graph and shade out the unwanted regions. If you're drawing this on the graph, they require that you use a scale of 1 centimeter to 1 unit on each of the axis. And here we are given the cost of operating each type of lorry: 5,000 Kenya shillings for lorry A and 12,500 Kenya shillings for lorry B. So the task in part C is to determine the number of trips each type of lorry should make in order to minimize the cost of transporting the hard code. And then we must calculate the minimum cost. So we go through the same steps. First of all, we see that the decision variables are given, so we don't have to look for them. Then we start plotting the constraints. We start setting up the inequalities. So for the capacity of the lorries, we said each lorry carries, type A lorry carries 8 tons. And if they make X trips and there are 3 of them, this is the total amount in tons that the lorries will carry. And the same for type B. The type B carries 15 tons. There are 2 of them. And if they make Y trips, this is a total in terms of tons that they will carry. Now the contractor has to deliver 240 tons. So it means they cannot be less than 240. So this means this gives us an inequality, 24x plus 30y is greater than or equal to 240, but this can be simplified to 4x plus 5y is greater than or equal to 40. I think you divide throughout by 6 and you will end up with this simplified inequality. So this gives us a capacity constraint. Then there's a trips constraint, which says the number of trips made by B should be less than twice the number of trips made by A, and that is captured in this inequality. Y is less than 2x. So the type A lorries should not make more than 6 trips. So we have X is less than or equal to 6. I think that's all the inequalities we can obtain from the problem. There's no more to add. So we graph again the same way. We start with the initial one, 4x plus y is equal to 50. Determine which side it becomes our borderline. Then we determine which is the unwanted side. Turns out that this shaded side is unwanted side. Then this is a strict inequality. Y is less than 2x, so it's drawn as a dotted line. That means the points that are precisely on this line, y is equal to 2x, are not part of a feasible region, but anything on this other end to the right will be part of the feasible region. So we have one last constraint, that is x is less than or equal to 6. Now we say the type A lorry cannot make more than 6 trips. So that gives us this last line as the border, x is equal to 6, and we need x to be less than or equal to 6. So the wanted region should be on the left of this line, and the unwanted region is to the right, and it is shaded out. So the feasible region is what is inside this unshaded region. So the points that we wish to look at to minimize the cost should be the corner points. Now there's only one corner point here, or one vertex, that is feasible. You see the other one, this is a strict inequality. Y was supposed to be strictly less than 2x. So the points on these two points will be part of a feasible region because they lie on this line, and we have a strict inequality for that constraint. So we have to look at points away from this line. The only corner point we have that works is this one. So let's see what that means. type A, truck, and 12,500 was the cost, I think, for each type B truck. So this is what we wish to minimize, and that is what part C was asking us to do. So we shall do this by inspection. Just simply check the points. So as we saw in the earlier diagram, the only feasible corner point has non-integer coordinates. So if you look at the diagram here, this corner point has the coordinates will be 6 and 3.2. So we can't use that because we can't get 3.2 trips. We need a whole number for that. Usually what happens in such a case is you consider the neighboring points. There's something else they normally call boxing. So you would just consider this box around the point at the corner and then look at the neighboring point. So the points down here cannot be considered because they are not in the feasible region. We can't consider this one because it's in the not in the feasible region, but these two, this one here and this one, are in the feasible region. The rest are also in the feasible region, but I think ideally you want to look at the points that are close to, integer points that are close to the vertex. Some people call this thing boxing. You box in the point. So we are going to try to evaluate the objective function at these other points which have integer coefficients. So the one that gives us the lowest cost is what we take as our optimal point. So when we do that, when we compute the objective function at each of those points, we see that the 0.54 is what gives us the lowest cost. So we have completed the problem. We have the lowest cost and also the optimal point where x is equal to 5 and y is equal to 4. So each of the air lorries will make 5 trips, which satisfies our constraint where x was supposed to be less than or equal to 6. And each of the type B lorries will make 4 trips. And that solves our problem. There are other techniques. There's something called integer programming that is beyond the scope of this talk, but integer programming will give you integer solutions to such a problem. Then you will not have to worry about this decimal, these fractional points, like 3.2. But that is, for now, the best you can do is do the boxing, look at the neighbors around the optimal point, and evaluate the objective function at those points and pick up which one gives you the minimum value for the objective function in this case. So that brings us to the end of the class for this. I hope it was useful, but next week we should be back to the Olympiad mathematics. So today we had to cover a syllabus topic. This we don't examine in the Olympiad, but it was a request from some of the people who were there last time. But the recording shall be available. It appears many were not able to make it for the class, but the recording will be made available on YouTube. And the previous recordings are also there if one wishes to watch. So that's if there are no questions, comments, we will stop there for today.